and welcome to the 15th tutorial in the Jabrah reinforcement learning series. So today we're going to be talking about something we know as temporal difference learning, and we're going to be looking at it for the prediction problem as usual. We start with the prediction problem, then we go to the control problem. So this idea of temporal difference learning, you can think of it as a new reinforcement learning algorithm, because we've already explored like dynamic programming methods such as policy iteration and value iteration, and we've also looked at other methods such as Monte Carlo simulation in the last few lectures. So this idea of temporal difference learning is central and novel to reinforcement learning. So actually getting an understanding of this method will open us to a pool of much more reinforcement learning algorithms which tend to be more powerful actually. So it is a combination of Monte Carlo and dynamic programming, and you'll see how we are able to combine these methods to form a new way of solving for our reinforcement learning problems. So let me just denote that first, that this is a combination of Monte Carlo and dynamic programming. Right, this is an important note to actually take down. So the idea here is that, like Monte Carlo, temporal difference learning can learn directly from raw experience without a model of the environment's dynamics. This is one aspect that will be taken from Monte Carlo. And like dynamic programming, temporal difference methods update estimates based on part of learned estimates. So if you remember the idea of bootstrapping that we introduced in dynamic programming, where you try to learn a guess from another guess, we call that bootstrapping, and this is what temporal difference learning methods do as well. So in this video, we're just going to be looking at this algorithm for the prediction problem. And in future lectures, we'll start looking at it for the control problem and so on. So first of all, we're going to look at TD prediction. Right. Sorry. So TD prediction. Okay. So what is this mysterious temporal difference learning now? So first of all, whenever we're dealing with a prediction problem, the first thing we know is that what are we trying to do? We're trying to estimate V pi given our policy pi, right? This is what we do anytime we have a prediction problem. And we're going to make use of a certain update rule that we looked at in the previous lecture from Monte Carlo to give us a basis of how we solve for this prediction problem. So for Monte Carlo, right? So for Monte Carlo, we said that we update our value function as, say, VST, right? Would take the value. Let me just I'll try to insinuate anything here. So VST will take the value V of ST plus alpha. So you should be familiar with this formula from the previous lecture. So GT minus VST. So this is quite similar to what we were calling our incremental update rule from for Monte Carlo in our previous lecture, the one that we see here. We had called this the incremental update, right? But for in the previous lecture, of course, we had alpha being corresponding to the weights when we're looking at importance sampling and so on. But for this lecture, we're going to consider alpha to be constant. And we know this method, like if we choose alpha to be sufficiently constant, and by that I mean alpha to be an element, or say to be between say 0 and 1, right? We can denote this as constant alpha Monte Carlo. So we can think of alpha as being some kind of learning rate, if you're familiar with machine learning concepts. So we'll just assume that alpha here is just some constant. So one thing is that Monte Carlo waits until the end of the episode to update VST, and the reason why it waits until the end of the episode, because it's only at the end of the episode that we have this value here, GT, right? So we only get this value at the end of the episode, right? And this is what we do for Monte Carlo, but for TD methods, we actually wait until the next time step to make this update, which is analogous to what we do in dynamic programming. So let's actually look at the update rule for TD methods, right? So when we're talking about TD method update rule, so of course this can change based on the kind of TD method we're talking about, and I'm gonna go into that later on. But in general, we can update our value function as VST, right, to be equal to the same VST plus alpha, right, our constant parameter here that we denote as the learning rate, RT plus 1 plus gamma VST plus 1 minus VST. So this would be our rule. So if you are already familiar, if you watched the previous lectures on dynamic programming and so on, this update rule by itself should already make sense to you in some way. So immediately after we actually get our reward, in the next time step, we already make this update where we say that VST, we're going to collect RT plus 1 plus gamma VST plus 1. We don't know the real value of this yet, which is why we're actually doing this bootstrapping. We're learning a guess from a guess. So the target for Monte Carlo, if we look at Monte Carlo target, so when we look at Monte Carlo, let me use a different color here. So when we look at Monte Carlo target, we see that it's actually GT, right? But when we look at the target for temporal difference learning, we see that the value, okay, it's given over here. It's RT plus 1 plus gamma VST plus 1. That's what this target is in the case of temporal difference learning. So this algorithm, this update rule that I showed you here, actually it has a name. It is known as TD0, right? And another way of denoting this is, say, one-step TD, I suppose. One-step TD. That's what TD0 is. And we will look at like more generic like n-step TD methods later on. But for now, this is just an introductory lecture to familiarize you with what temporal difference learning methods actually are. So having said that, let's actually look at the algorithm for temporal difference learning for the prediction problem. And you'll see that the algorithm itself is actually quite simple. It's not so different from the Monte Carlo prediction, with the exception that just the way we update our value function, we're not waiting until the end of the episode. We're just waiting until the next time step, at least in regards to that. So I'm just going to quickly go through this. So our input is our policy pi, right? Which is our policy to be evaluated. And we have also alpha, right? Which is between 0 and 1, and we call this our learning rate, or let's just say our step size, right? So we're going to initialize VS for all S is an element of S plus arbitrarily. Okay, so these are the same steps that we do whenever we're looking at these algorithms. And the next thing we're going to do is we're going to loop for each episode, right? So still similar to what we're doing in the Monte Carlo version of this. So we loop for each episode and we initialize S, our state, right? And then we now loop for each step of the episode. And here we're going to define our action A to be equal to pi of S, right? Because we're given the policy here. And we're going to take action A, and after taking action A, we're going to observe our reward and the future state S prime, right? So these are the steps of the algorithm. So after that, which is actually the core of this whole video, we look at the update rule, right? We update our V of S by using the formula we discussed before. So V of S is equals to V of S plus our constant alpha, which is our step size, multiplied by R plus gamma V of S prime minus V of S, right? This is how we update, and now our S becomes S prime, and until S is terminal, right? So this is basically what the algorithm is for doing this. And this here in green, so this here, this is just our update rule. This is what we're calling our update rule for this. Okay, so we look at the algorithm. It's pretty simple. So one thing we can actually look at already is, this is coming from the previous lecture. So when we're given, like, say, V pi of S, we say that at least it's the expectation, right, of a policy pi of GT given ST is equals to S, and this is equal to the expectation of a pi of RT plus 1 plus gamma GT plus 1 given ST is equals to S, equals to expectation of a pi. So this is something you should already be familiar with if you've been following these lectures to begin with. So we have gamma here times V pi of ST plus 1 given ST is equal to S, right? So this is our update rule. So in the case of Monte Carlo, right, we consider this to be an estimate because we don't have the true value of GT, right? But what we're doing is we are sampling. We have a sample update, right? Like, we're sampling the value of GT in the current let's say step. We don't know, in the current episode at least, So we don't know the true value of gt, right? So since we are actually just getting a sample, we call this an estimate of that's what the expectation actually is. But in the context of dynamic programming, right, we're not looking at dynamic programming, this isn't an estimate for the same reason, because in the case of dynamic programming, we have a model of the environment. So this becomes an estimate because we don't know what the true value of v pi s t plus 1 is, right? So since we don't know the value of this, then this is the reason why this is an estimate. And there's a reason why I'm actually talking about this. It comes down to something that we call sample updates and expected updates. So because I'm telling you why for Monte Carlo we call this an update, and for dynamic programming why we call this an update, like the different reasons. And interestingly, temporal difference learning methods are updates for both reasons, because in temporal difference learning we are both sampling, right? Because we don't have a model of the environment, which is why this is an update. And at the same time, we're also making a guess from another guess, which we're calling bootstrapping, like they do in dynamic programming. So this gives us things that we know as, so we've got a sample update, right? Like we do in, and this applies to Monte Carlo and TD methods, right? And what a sample update is that we have our state here, right? I'm gonna draw the backup diagram here. So we have our state, and we take an action, right? And then we end up in a new state. So we start from a state, we take an action, and end up with a new state. And we're gonna use the value of this new state, at least in the context of temporal difference learning. We're going to use the value of this new state plus the reward function, the reward value that we collect along the way, to update the value of this. So if this is state S and this is state S prime, and then we get some reward R here and there's some action A. So what we're doing to update the value of S is we look at the reward that we collect along the way and the feature value of S prime to update this S. So we know this is a sample update because we're updating based on the single sample. But now there's something else that we already talked about in the previous lectures known as the expected update, and this particular thing applies to dynamic programming methods, where we say we have a state S, right? And then we have a lot of potential candidate actions, right, that we could take, right? And for each of those actions, we might end up in a different state S prime, or another different state S double prime, and so on. And this goes on for everything else here. So we already discussed before what the expected update is, but basically what we're doing is we're not using a single sample to update the value of S in the case of dynamic programming methods, right? This is for DP. We're not using a single, we look at all these actions and their corresponding probabilities, because we'll have a probability of taking this action here, we'll have another probability of this action here, another probability here. So we look at each and every one of these probabilities, and we compute the expectation, right, using the Bellman update. So this is how we actually update our state here. In the context of dynamic programming. So it's important to know the differences here between, say, the sample update that we see in Monte Carlo and TD methods and the expected update that we see in dynamic programming methods. So I thought that information might be useful for you. So moving on. So now let's actually take a look at part of this equation that we're using when we're doing our Monte Carlo update. And we saw that we can do RT plus 1, right, plus gamma VST plus 1 minus VST. So one thing we can realize already is that, okay, this is just an estimated value of st, and we can think of this as like some kind of beta estimate, right? So that's one way we can look at this, and we're computing the difference between these two terms, this term and this term, and this we can denote it by using delta t, right? And this delta t, we call this the TD error, right? The temporal difference error, right? So as you can see, we can only calculate this error at time step t, only at time step t plus 1 after we actually collect our reward, and we'll look at the value of v of st plus 1 and so on. So having said that, so the thing is that if the array, if our v array does not change during the episode, like what we see in Monte Carlo methods, like we're not changing the value during the episode, only at the end of the episode, then the Monte Carlo error can be seen as the sum of TD errors. So it's important that I introduce this concept right now, because it's gonna become it's gonna become very useful later on. So what we have here is that we can say gt minus vst, right? And we know this to be the Monte Carlo error, right? From what we saw, say, I guess in the first page here. Right here. This here is our error in the case of Monte Carlo. So we know this is our Monte Carlo error. And we can write this as rt plus 1 plus gamma gt plus 1 minus vst, right? Which is quite similar to what we already have here, plus gamma v gamma vst plus 1 minus gamma vst plus 1. Okay, so I just added and remove the same term here, so this is essentially equal to 0, but it's going to be important, of course, for proving this. So this is actually equal to so rt plus 1 plus gamma gt plus 1 minus vst, we call this delta t, right? Essentially, sorry, rt plus 1 plus gamma vst plus 1 minus vst, we had called this delta t. So this is equals to delta t, delta at time step t, plus gamma gt plus 1, gamma gt plus 1 minus vst plus 1. And you can already see that this is starting to look like what we have over here, and this is equals to delta t plus gamma delta t plus 1 plus gamma squared gt plus 2 minus vst plus 2. So as you can imagine, this will continue like this. Like I hope you can already see what the pattern is here. It should be pretty clear and easy. And once we're at this stage, we say this is equal to, let me write this equal sign better. So delta t plus gamma delta t plus 1 all the way up to gamma at time step t minus t minus 1, say, of delta capital T minus 1 plus gamma at time step t minus t of g capital T minus V S capital T, right? So this is at the final time step. So at the final time step, we can just think of this being just 0 minus 0, right? And this should give us at the end the summation from k is equal to t up to capital T minus 1 of gamma k minus t delta k. So this is essentially our summation of TD errors that we have here. Let me highlight it in a different color. So here, right, we're summing up the TD errors by looking at this Monte Carlo update. So the thing is that this identity is not exact if V is updated during the episode, because again we made the assumption that V does not change during the episode. So if V is changing during the episode, like in temporal difference learning, this identity is not really exact. But if the step size is small, this identity will hold approximately, right? If we use a small step size. And we'll see why this whole analysis we're looking at here is important. I just wanted to introduce the idea behind it because we're going to explore it further in future videos. So the advantages of TD methods, let's actually look at why we're actually using this method. So one thing I'd already mentioned is that there's actually no need for a model of the environment, just like in dynamic programming. And just like in Monte Carlo, it's naturally implemented in an online incremental fashion. So some applications may have very long episodes, right? And other ones may have continuing tasks without any episodes at all. So in cases like that, it's actually nice to have this incremental way of updating our value function without waiting for them to without waiting for an episode to terminate, or in the case that we don't have an episode, like how would we do it using like methods such as Monte Carlo and so on. So it's nice that it can capture both the advantages of dynamic programming and the advantages of Monte Carlo to have one much more powerful algorithm. And we're going to see how powerful it is in the future videos. But for now, I think this is okay for an introduction. Thank you very much for your time.